Oopsie. Oh well. It was mostly recap. Anyway, so I don't want to be too like making up facts, but if I recall correctly, it's because the guy who made it up tried to come up with system A, B, C, D, E, and then F is the one that finally ended up working. So I think that's what it's from, but I'm not 100% sure on that. Anyway. Yes, so this is the implementation of the identity function in Haskell up here. And then here is what you would write basically in system F. So ID is just some like variable name that I'm using. It's not really there's no concept of function declaration, but I'm saying that ID is equal to this thing, which I'll explain. And it has type for all alpha, alpha to alpha. So typically we use alpha for these type variables, and we use the for all symbol instead of the word for all, but that's just syntax. It doesn't strictly matter. Yeah, so like I said, system F is based on lambda calculus, but it's much more powerful. So to give a sense of this, one thing is that we used to have to include Boolean or something to have any types at all, basically. Now we have now we don't have Boolean anymore, and we also got rid of product types and some types. But as we'll see a little bit later, we actually can define all those things in the language itself. We won't need to extend the language at all to have any of these things. We can also add lists and numbers and lots of things. And the other thing I want to point out is that this language is like deceptively simple. It looks like the additions you make look like they don't really do a whole lot. So for example, like after we talk about it, it'll probably be unclear how you can suddenly have lists in this language when there's nothing looks like lists or anything. So my advice for doing these sorts of things is just to sort of like let it like wash over you once, and then try and like implement things in the language, and that will sort of give you a sense of how it works. But basically, don't get too caught up on, I don't understand why this thing exists. That works for me anyway. So the syntax is down here. It's very similar to before. So for types, we have function types, just like before, but we have two new kinds of types. So we have type variables, which we write alpha, beta, gamma, etc. And then we have this quantification. So for all alpha, tau. And then for the expressions, we still have variables, we still have lambda expressions, and we still have function application. The two new things we have are we have this is a capital lambda, alpha.e, and e applied to tau. So these are type abstractions. This is a type abstraction, and this is a type application.
Hey, Reed, quick question. So for tau, I know, so I think it's not connecting the dots. The universal quantifier for alpha dot tau, what does that do?
Yeah, so it's saying also if I have like for all alpha to alpha, it's saying for any type alpha, I will get whatever the thing is. So I'll go get a tau. So in this case, for any alpha, I can get a function from alpha to alpha.
Oh, okay, interesting.
Yeah, so it's kind of like, it's kind of like if you had like a function in Java that was like public t, like f t x, like this, or maybe you should have the generic thing. So it's saying, for any type t, I have this function that takes an f and returns an f, or it takes a t and returns a t. And this is, we're choosing alpha instead and writing it slightly differently because conventions. So yes, so evaluation rules, we have all the rules from before. So we have the congruence rule, we have beta reduction, we have alpha conversion. We also technically need alpha conversion for these type abstractions because, I guess it kind of is called alpha conversion because we usually use alpha for the variables, but it's different. Anyway, so the only new evaluation rule we need is this one. So like how the lowercase lambda gives you functions, just like regular functions on expressions or terms, The capital lambda gives you a way to do sort of functions on types, basically. So when we apply this function on types to some type, we substitute the type for the argument name. So I'll give an example at some point of this, but this is saying if I have the identity function, which is this, and I apply this to some type, like say nat, so now I have a function that takes a natural number and returns the same thing. So I'm using the same substitution syntax, substitute tau for alpha in E to also work for types. And yeah, and the last thing I want to point out is, yeah, so this step of evaluating type applications or type abstractions, or applications of types to type abstractions, is like a type checking thing, but not something you actually need to do to evaluate it. So if you wanted, you could just get rid of all of these and the program would actually run fine. So one of the ways that people define the semantic choice language is sometimes to say, you know, what this program does when it evaluates is the same thing as what this program without type annotations would do in the n-type lambda calculus. And then the type checking is eliminated, which is kind of nice because it's like fewer steps usually to evaluate. But I'm going to leave it like this because I think this is clear.
So Reed, at a high level for the language, that's what, so this is essentially what gives you generics for, I mean, you can have any number of arguments, but just generics for functions.
Yeah.
Okay.
Yeah, so this is saying, you know, I can specialize this type or this term E to any type tau. And when I specialize it, I get, you know, I get functions on whatever type, or, well, that's basically all we have. Basically just have functions. So you get functions on whatever type. For the type rules, yeah, so all the type rules are the same as before, except for, or not except for, but we also add these two new rules. The only difference to the way I had before is the gamma before was just a list of variables and their types. Now we're gonna say it can also have type variables like alpha in it. And all that means, or the only reason for doing that is that we don't want to bind the same type variable twice. We want to do like lambda alpha dot lambda or big lambda alpha dot big lambda alpha, because then when we substitute something for alpha, it's not gonna be clear what you actually do because there's two alphas. So the convention is basically you can't put something into a type environment twice, and that's a convention that prevents you from doing that. So this first rule, the type abstraction rule, or the left rule, I guess, not first, says, so if I have a big lambda alpha dot E, its type is for all alpha dot tau if this E has type tau in the environment gamma. So E is going to be some expression that will work, will give you type tau for any alpha. So later when we substitute in for alpha, we're guaranteed to get whatever type we would have gotten had we treated alpha as that type. We will run a program in a second, and that will make it clear, I think. And then the last one is through type abstractions. We also type applications. So if E has type for all alpha sigma, why do I use sigma? Oh, because I used tau down here. Sorry, so if E has type for all alpha sigma, then when I apply E to this type tau, or specialize it with the type tau, then I get sigma, but with all the alphas replaced by tau. So let me go back to, let's just, do I have an example? Yeah, I'll talk about that in a second. Okay, so let's do a slightly different function. So big lambda alpha dot, say x has type alpha, y has type alpha and returns x or something. There's not a lot of functions you can write that aren't long, but So let's say this is our function, this is f. So the type of f is, actually, does anyone want to guess the type of f? Okay, so let's see. So the first thing here is this big lambda, which matches this rule or this rule. So it's going to give me something that's for all alpha. And then in here, we sort of treat it just like a normal, like we would normally in lambda calculus, except we have these alphas. But if you just sort of go through the same motions, so you say takes one argument that's an alpha, and then another argument that's an alpha, and then returns x. X has type alpha, so it returns alpha. So this is the type of f. And if we were to evaluate it, let's say we do f. I don't know. Bool, true, false. So because it starts with a big lambda, we have to specialize it with some type. So we have to tell, basically we have to tell what alpha is going to be. So alpha is going to be bool in this case, and then I'm passing in true for x and false for y. So when I evaluate this, I get, well, I'll end up getting just x, which is true, but sort of intermediate stage. X has type bool, y has type bool, and I return x, supply to true and false. And this is exactly like in the simply type lambda calculus, you just get true out of that. Does that make sense? Okay, well, I'll move on, but if you have questions, please stop me. I'm gonna skip that, okay. So before we do more examples, system F stuff, I wanted to just say a few things about it, which is, so yeah, in some sense, it's sort of more powerful than Haskell's type system because you can do, I mean, there's things you can do in Haskell you can't do in system F, but you can put the for alls anywhere you want, which maybe doesn't seem so powerful, but we're going to use it to implement all these data types like pairs and lists and stuff in ways that you can't do in regular Haskell without enabling language extensions. The problem with doing this is that because we can have the for alls everywhere or anywhere we want, it actually makes type inference undecidable. So in Haskell, you use type inference all the time. One of the reasons they didn't want you, or they don't want you to put for all anywhere you want, is because it makes type inference, well, impossible, but much harder even when it's possible. But it's much nicer because, for example, in this previous thing here, I mean, you have to write these annoying like type annotations, like, oh, this thing's going to, you know, alpha is a Boolean here. In Haskell, we could just write f of true and false, and it would be like, oh, so alpha is going to be a bool. Which is much nicer, especially when we do more complicated examples. You'll see there's a lot of these annotations that are very tedious. It also makes things longer and makes evaluating them annoying. But it also makes the language very powerful. So that's sort of the trade-off we get. Yeah, and yes, so this other thing. So there's this idea in Haskell and other languages like it called free theorems. Which is basically the idea that these types are actually very restrictive. So the type like for all alpha, alpha to alpha is actually so restrictive. There's actually only one function that has that type, which is the identity function. So actually, if you know that f has type for all alpha, alpha to alpha, it could only be the identity function or something that's like equivalent to the identity function. So you can prove this. There's this paper from 1989 in the footnote. It's called Theorems for Free. You'll see it actually takes a bit of work. It's not exactly for free, but you know, such is life. At any rate, the sort of intuition here. So let's look at this first example. So if f has type for all alpha, alpha to alpha, then f is equivalent to this term. This thing is the identity function, the polymorphic identity function that works for any type. And the intuition here is that if I have to write a function that works for any alpha, and I have to produce an alpha given an alpha, obviously the identity function is one implementation I could have. But if you think about it, there's no other implementations because there's no like default value for types that you could use to just, you can't say like return null or something, right? Like in Java, you could do return null for some like generic type function, but there's nothing like that here. There's no way to get a value of whatever type without knowing something about that type or already having a value of the type. So in our case, we have a value of the type, and we can't get alpha any other way, so you have to return that one, and that's the identity function. That's like the informal argument for why there's only one function with this type. The proof is longer. And,
Agreed.
Yeah.
When you say there's only one function with this type,
yes.
Maybe I'm just like misunderstanding, but when I think of like a function that takes in an integer and goes to an integer, you can have like an infinite number of functions, quite literally, like you could have x plus 4, x plus 5 returns a different result, still the same type. Do you mean something different?
Yeah, so yeah, for functions from integer to integer, you can, as you say, you certainly have infinitely many of them. But functions that for all alpha take alpha to alpha, there's only one. So for any particular alpha, there's usually going to be a bunch of functions from alpha to alpha. But if you want one implementation for all alphas, then there's only one.
Oh, I see what you're saying.
Yeah. Yeah, and then you can do more sorts of things like this, which is, so you can say, so for example, you say for all alpha and for all beta, the type of pairs of alphas and betas takes in a pair, returns something of the type of the first thing in the pair. There's also only going to be one function that does that, which is just going to be the function that gives you the first thing. Say a little bit more formally, what I'm saying is, this is sort of the easier to read version down here. What I'm saying is that if I take whatever function has this type, I'm calling it first because that's intuitively what it is. If I do G after I do first on some pair, it's the same thing as just doing G on this first thing in the pair and then taking first. So just knowing the type of first, I know that that's going to be true, which is, again, something you get from this framework of free theorems that is developed in the paper. And there's, you can do this for lots of things. So if you have a function that does A to B to A, what it does is it takes two things and returns the first one and ignores the second one. There's just no other function that has this type, which is basically the same argument as the identity function, except now it has an extra argument that it will ignore. So this is occasionally useful. It's somewhat less useful in real programming languages because, in Java, for example, you do have null. So you don't know it's the identity function. It could just be like return null. But it's interesting, I think, and it is sometimes useful for reasoning about programs. So that's all I'll say about that for the moment, unless there's questions. Yeah, so now I will speed through implementation of system F in this language called mod, which I think I briefly talked about at one of the previous meetings, but basically mod is, it's a sort of functional-ish language that is built for implementing and proving / checking things about rewrite systems, which is one way to view a programming language. So we define three things, three sorts. This is going to be for our syntax. So we have expressions, we have typevars, type variables, and we have types. QI, then we say here we define these relations between the sorts. So QID is quoted identifiers. So it's things like X or like Y. Basically, they're like strings, but they're in this way instead. And then we're saying type vars are some sort of types, because alpha is a type variable, but it's also a type on its own. And then I'm going to define 3 constructors or values for type variables. So op is how you define a function. These functions take 0 arguments and return a type variable, but I'm going to leave them unimplemented. So they're basically just constant symbols. So alpha, beta, and gamma are type variables. And now here's the syntax for types and for expressions. So we can take 2 types. So that's what, so this underscore here, this underscore here, they've re-underscored. Those are the arguments to this operator. So this is like tau1, this is tau2. And so it takes in 2 types, tau1, tau2, and gives you another type. And for all, it takes in a type variable and a type and gives you another type. And then lambda has QID, which is what I'm using to represent my variables, a type and expression, and it is an expression, and so on. So for example, so if I write this, I'm not going to underline the whole thing, but so if I write this, mod now, it understands what this means. It knows that this is an application at the top level, because this is true, and then this big thing here is a function, and then it's a type application because of square brackets, and so on. Okay, so far we haven't done anything except defined the syntax of the language. Now I will add the evaluation rules. So I'm not going to show the substitution, how you implement substitution, because it's kind of long and tedious. I'll put the code somewhere so you can look at it. But here are the rules that implement the evaluation part. So we have beta reduction, which takes some lambda, so some lambda x, some type t, body E1. And I mean, I don't know if I actually need to rewrite this because it really is basically the same as the notation we've been using. And becomes E1 with E2 substituted for x. And the substitution is something I defined earlier. And then for same thing for type application, basically, we have this big lambda A. I'm not using like capital lambda, I'm using this thing because it looks like a capital lambda. I have this big lambda A dot E, and I'm specializing into some type T. All I do is I have E, but with T, both A replaced by T everywhere. And that's that. For type checking, I have to also add type environments. So we have nil, which is like an empty type environment. We have this operator, which is the, x has type, whoops, x has type tau. You just build these assertions or pairs that x is type tau. And this will give you a type environment with just one thing in it. And then we can use this comma operator to combine type environments. So, x is type tau as type environment, y has type sigma as a type environment. I use the comma to put them together, and I still have a type environment. And I've said that this operator is commutative, associative, and its identity is nil. So basically, the point of doing that is because it gives a way better pattern matching. So, we write all the rules as, for example, x, gamma x is type tau proves x is type tau. This is the var rule. If gamma was like a real list, then I would have to do something. I would do like say like, if x is in gamma and like search for it or like reorder it or something. If I tell mod that this operator is commutative, associative, and this identity is nil, then it will do the reordering for me whenever I need it. And then the last thing is this type judgment. So it is a slightly different form. Normally we would write this, but the mod version works like this. This is a function and it will evaluate to the type of E. This is easier to work with when you're actually programming, but it's the same sort of idea. And now,
I don't know if I'm completely following you anymore. Like I get what you're saying, but could you just
Mhm.
like summarize what this slide is letting us do?
Yeah, so this slide, so we're defining type environments, and then we're defining this. I mean, this is the function essentially we need to implement to do type checking. Because when I call this function, if it gives me some type, then the program or the expression is well typed. And if
Mhm.
it fails to evaluate, then the program is not well typed.
And the other two, like with the comma and the colon. Well, the colon,
Yes.
yeah, yeah.
Sorry.
No, you go ahead.
Okay. Yeah. So all these three things actually are just defining type environments. They're saying like how it works. So the first one is, if I want to have an empty type environment. The next one is if I want to have a type environment with just one thing in it, or if I want to like, yeah. And the second, the third thing is if I want to combine type environments. So I want to add a new variable to type environment, or I mean, I could even combine two like whole type environments, but I'm not actually going to do that.
Got it. Cool.
Let's see. Simply, okay. Anyway, so here's the type rules from simply type lambda calculus. So we have the variable rule, which is before we had this. Again, we just change it so it evaluates the type of x, which is still tau, or t, I guess, in this case. Yeah, so the rule is basically the same. These rules, so RL is short for rule, CRL is short for conditional rule. So this is saying, this ABS abstraction rule is saying, so gamma proves lambda x has type T1, and the body is E2, is a function from T1 to T2 if gamma x has type T1 proves E2 has type T2. It's sort of a reversal of the order that we normally write them in with the premises on top, but it's basically the same with this arrow becoming, or with the colon, like the colon like here becoming this rewrite arrow. And for the application rule, again, so if we apply a function E1 to some argument E2, it has type T2, where E2 is the argument type and E1 is a function from T1 to T2. So if both of these things hold, then the whole expression has type T2. This thing, yeah, so this thing means and. I'm also using it, I guess, in my language, but this is just the sort of logical symbol for and that you use in mod.
Wait, so what does that mean? It's like T1 and what?
Oh, yeah, it's gamma proves E2 has type T1 and gamma proves that, yeah. I could have put the parentheses, but I usually like to have as few parentheses as possible, which is maybe not the best for reading. But anyway, yeah, and then these last two rules are the rules for system F. They're this type application rule, which is the same as before. Yeah, and type abstraction rule is also basically the same as before. I want to move on because I do want to talk about more things than just the implementation. I don't know, just believe me, the implementation exists. And when you use it, you get this. So for example, so the way that I type check something is as I say rewrite. This is gamma, in this case it's just empty. And this is the expression. So when I rewrite this, it will rewrite to a type if the expression is well typed. And if it's not well typed, it'll get stuck. In this case, this one is well typed. This is the identity function. So it gives me its type, which is for all alpha, alpha to alpha. And if I do this more complicated one, I get a more complicated type. So yeah, I'll put the code up, but it's half how you implement system F and half commercial for mod. So anyway, so this is sort of, I guess, last thing we're going to talk about because not that much time. But so church encodings, we briefly talked about these. I don't know if I use the word church encoding, but that's what these are called. It's encoding sort of data types as lambdas and functions. So here's part of how you do Booleans. And then basically the sort of guiding principle behind understanding these is that you define them how you use the values of the type. So the thing you use Booleans for is if statements. I mean, you can do them for other things. Basically, they're if statements. So the values of type Boolean should be basically if statements. So they take in two arguments, like a then thing and an else thing. And if it's true, it returns the then thing. And if it's false, it returns the else thing. So that's what these do. These are untyped lambda calculus terms. We'll do the system F ones in like one slide. And hopefully remember how these work. So, oh, this is what I just said. Yeah, so, this is how you use Booleans. But instead of writing this, essentially we want our Booleans to work, so we can write this. And it does basically the same thing. So would anybody like to translate these untyped lambda calculus versions to the system F versions? I mean, just the first one or whatever you want.
Wait, so what would we have to provide here? Like a types for the input and output, and then a definition?
You need to, yeah, I mean, basically, so, well, yeah. So these lambdas here they don't have types on the arguments. So it will have this basic structure, but you need to have like, it'll be like X and then something, Y, something, and then X. And maybe other things. But but this is definitely part of the answer.
Wait, do we have to constrain these to like Booleans, or is there like some way we have to figure out to do that?
So the X and Y are not Booleans. They could be Booleans. They can be anything. The true and false is the Boolean. So this whole thing will have type bool. We haven't actually defined bool, but whatever type this thing has is going to be with the type that we call bool. But the X and Y's will be, anything.
Okay. Wait, so then would we do this by like our, let's see, type abstraction? So we do like lambda alpha at the beginning.
Yeah, like and
then
alpha, like that.
Yeah, and then dot. Yeah, and then X and Y would both, I guess they don't have to be of the same type, but like they could be any, like, I was gonna say like lambda X is of type alpha, X is of type alpha, and Y is also of type alpha, but I don't think it has to be.
Yeah, maybe also have like a beta, like a lambda beta at the front, or
beta thing like this.
Yeah.
And make this beta.
Yeah.
Yeah. Okay. So yes, this is a very good guess. So you're actually right that alpha or Y actually has to be alpha 2 for it to really work as a Boolean. So the reason for that is because we want true and false to have the same type. So if we do false as, if we were to do this alpha beta thing, alpha X is type alpha, Y has type beta, return Y, then now true is like alpha to beta to alpha, or would be with the old formulation, and false would be like this. So the types of the two, so the Boolean type has like both of these different types, and we want to be able to use them as if statements, interchangeably, basically. So just how sort of in Haskell or other languages that have expression or if expressions, you need both branches to be the same type. You also have to have both branches of these Booleans be the same type. So these have to be alpha and alpha. Does that make sense? Yeah, so this is what we came up with last time, or 2 seconds ago. Here's how you write it in mod, using the same implementation. So we have, I'm just defining this abbreviation for bool, which has this type. And then I have true and false, which are the exact same implementations as before, just converted into the mod form. And I also did and. And now if I like evaluate something, so and true, so what is this? This is true and false and true. So that's false, of course, because there's this false here. And when I evaluate it, I get this thing, which if you look at it, you'll see it's a function that takes, well, over any type alpha that takes 2 arguments, which are called 0 and 1 because those are just automatically generated. And it returns the second one, which is what false does. So this is false. So yeah, unfortunately, you don't get like nice names. It doesn't like say, oh, this is false, but it works like false. Okay, so yeah, I will introduce this, I guess. So before we spend time adding new rules, typing rules, and evaluation rules to have pairs, now our type system and language are strong enough that we can define pairs in the language without adding anything new. So following our vague principle of, you should define these things so that a value of type pair is a function that describes how you use pairs. So the way you use pairs is you do something, or you write a function that takes in 2 arguments, basically, the first thing, the second thing, and it does something with those arguments. That's broadly how you use pairs. So this is a Haskell implementation, which is much cleaner than what I'll put on the next slide, which is the actual system F implementation. What I'm saying is to make a pair of A and B, what I do is I return a function. So this is a like lambda function. So I return a function that, given a function that takes an A and a B and returns a C, I just give this function the A and the B that I was given earlier, and then whatever it does, and it produces a value of type C. So this is sort of a trick to store the 2 values that will eventually be passed to the function in the lambda, basically. So, in a more conventional language, what you would do in F is like, pattern match on the pattern match on AB to get it out, or use like first and second. This way also works, but it's nicer for our purposes because we only need functions. So if you want to implement like first, so first x, y equals x, if you want to implement this, what you would do is you would say first x, y, sorry for mixing up x, y, and A and B, but well. So first, instead of taking in a pair, it takes in 2 arguments and returns the first one. So if I were to do first of make pair, let's say 1 and 2. So make pair. Wait a second. Sorry, this is in the wrong order. Should we make pair?
Wait, doesn't make pair return a function?
Yeah.
How does that make sense?
Well, let me just evaluate it. Wait, is your question how does a function returning a function make sense, or why is that the right thing?
No, wait, I'm confused about the input type of first.
Yeah, the input type. Okay, so first will be A to B to A, and so when I evaluate, so I make a pair with say 1 and 2 in it. And this is now a function. And when I pass first to it, which is sort of backwards of how we normally think about it, but this is how it works with this encoding. When I pass first to it, if I look at the definition of make pair, it's lambda
Oh, yeah, okay.
f 1 2 first Now first goes in for F. So it becomes first 1, 2, which equals 1.
Yeah, well, I get that, but I think earlier you wrote like first of make pair of 1, 2.
Yeah, I did. That was
I'm
wrong.
confused about that. Oh, okay, I see. Okay.
Yeah. It's very reasonable to be confused about that. Yeah, so this is basically how it works. This is what it looks like in system F. Do not be afraid.
Do not be afraid.
God.
Panic. Yeah, that would have been a better reference. But anyway, this is the same function, but with all the type annotations you have to have in system F. So for all alpha, for all beta, given an alpha and given a beta, you get a function that for any type gamma, given a function that uses an alpha and beta to produce a gamma, you get a gamma. And that's, if you think about it, that's the type. I'm going to use this abbreviation because I don't want to write the whole thing out all the time. So then the type becomes, given an alpha and a beta, you get a pair of alpha and beta, which is much nicer. But you have to know under the hood that it looks like this, because otherwise you will not know how to implement things using pairs. Yeah, and I would like to talk more about pairs, but it's 3, so I'm going to pause here, I think.
I have a quick question that's not really related to the lecture, but you know how, so I'm giving, unless you have anything left to say.
No, not really. I mean,
Okay.
I have 13 more slides, but
Well,
I would not say anything else.
yeah. Well, yeah. So 2 weeks from now, I was planning on giving a talk, right? So I don't think I might not be here next week. So I just wanted to like plug that now for Colin and Timothy. And I was planning on making it a little bit, I mean, it's not super technical. It's about my open source project that I did with ReasonML, which is just like OCaml basically. But I was going to try to open it up to other, I was going to post in the ACM chat because it's like, I was going to make it sort of like takeaways from open source development because the project did fairly well. Like it's triple digits in the stars, AKA between 100 and 200, which is like fairly successful. And I think I had some takeaways that might be useful to other people. So I was going to open it up if you're comfortable with that to just other people if they want to attend. And instead of like tailoring it to like be super technical.
Yeah, sure. I mean, yeah, that sounds great. I'm always happy to have more people, so.
Yeah, okay.
Cool.
Oh, wait, could I ask something for like scheduling purposes?
Sure.
So I also wanted to check out like SIG-IDA research, but they have the same timing as we do. So I was wondering, since we're like only a few people, are you guys like okay with like switching the time slightly?
I can switch times.
Okay. Like
I don't know. I mean, I don't know if everybody else can, but.
Okay. I hope this is not too inconvenient. Like I'm okay with literally any other time, but it's like, yeah.
Yeah, like still on a Sunday is fine, or?
Yeah, I was thinking, I don't know, we shift it like an hour earlier, an hour later or something.
Yeah,
Okay,
one of those two I think would be ideal. Maybe later.
Later, sure.
I'm out there.
Yeah.
That's
Okay.
fine.
Does that work?
Yeah, that's fine with me too.
Okay.
I appreciate it.
Yeah.
Cool. So 3 p.m. next week.
All right. Nice.
Okay, cool. Yeah, next week I will